My name's John McFarlane. I work at A9, and today I'd like to talk about numbers. Okay, so a couple of years ago I floated the idea of standardizing fixed point arithmetic, but the reference implementation grew and grew because I needed to prove that you can solve fixed point in isolation without designing yourself into a corner, and to do that I needed to take a stab at solving a bunch of other problems. So this is the talk about the problems and the solutions I've come up with in the library CNL, where I collect these solutions and work on them. I'm here to promote my efforts to standardize some of this stuff, and also to let people know about my library. But hopefully I've tried to structure the talk in such a way that I share some of the things I've learned about numerics along the way. Hopefully you'll you'll leave this talk slightly better equipped to avoid some of the pitfalls of working with C++ numeric types. But also, hopefully you'll clone my library and check it out. Okay, so to begin with, the problems that I'm talking about, I'd just like to go through briefly what some of them are. So firstly, the problem with integers, they only count whole numbers. They have a low fixed resolution. They have a limited range. And thirdly, well, this could be 3, 4, 5, 6, 7, 8, 9. There's a whole bunch of interesting things that integers do. Different types of integers do different strange things. They round strangely. They have different behavior when you run out of range. I'll cover some of these things as we go, but there's enough here for a very long talk on its own. So floats. Some of the problems with floats, they're complicated. They have their own strange behavior, and given you kind of associate floating point with doing math-intensive work, they do some things that are not very kind of mathematical. So, for instance, you switch the expressions on two sides of a multiply or add operation, and you might find you get a different result.
John?
Mm-hmm. Oh, you can't. Oh my goodness. Okay.
Thanks.
All right. Thank you. Thank you. Is that not working? Okay. Thanks. All right. You can see that all okay?
Yes.
Great. All right. Do you want me to? No, I'll carry on. Problem number 3, and believe me, this isn't a complete list, but a lot of people point out the functions in CMath or math.h are not constant expressions. So a lot of stuff you'd want to do at compile time in a const expr setting, you can't do for reasons that are kind of quite frustrating. Floating point values in the millions range have much lower resolution than floating point values in the tens. This is an aspect of their adaptability, but it can have unpleasant consequences. Basically, they're less precise than they seem. And fifth, this one comes back to the first point. Because they're complicated, they require many more times the amount of silicon, and consequently the amount of energy required to perform arithmetic in floating point is much, much greater than integers. And this has huge ramifications for embedded systems and in the cloud. And we're seeing a lot of applications that are very math intensive, deep learning, things where you have phone apps that do incredible things with neural networks and require to do huge amounts of computation on a very small charge, and so floating point does kind of eat a lot of power, and it can be a problem. So here's kind of my analysis of where we are, given those problems. We'd like to fix everything that's wrong, but it's a tall order, and so given the trade-offs, I've bitten off a chunk of work, and I hope to show you that it's a valuable one. I believe that floating points maybe have fewer issues than integers. At least they surprise and annoy people less. But integers are a very powerful abstraction over registers, and I mean they really are pretty close to the metal, but there's a lot of ways in which they could be improved. And so what I aim to do with CNL is I want to try and do for int what the STL did for built-in arrays, basically. It seems like a good goal to aim for. So I want to provide zero-cost abstractions over language-level features. Std array, it's one of the lowest level components of the STL, and here it's kind of almost a swap-in replacement for native arrays. In fact, it's virtually the same as native arrays, other than it solves a problem with decay, where you can't really pass arrays around as arguments because they decay to pointers, and that can be a big problem. Okay. Another great thing about the STL, it's familiar. If you already know how an array works, and you don't need to learn an awful lot about std array to start using it straight away. And it lets you opt into extra safety features. If they cost you runtime performance, you're not forced to use them, but you can. I had to actually look up that std array has an at function. So for anyone who doesn't know, in that second example, I extract the third element from A, and in this third snippet of code, I'm doing a similar thing, but the at function performs bound checking on the integer that it receives. So here, if the integer is out of range, if it's negative or beyond the size of the array, at will throw an exception, and incorrect code cannot be allowed to run. But that's costly. There's a runtime cost associated with that, so it's an opt-in. So most importantly, not generally most importantly, but for the purposes of a library called CNL, I want to make types that are composable. And the STL, we kind of take for granted just how composable it is. So I've just very quickly rattled up an example that just had a few pairs of angle brackets in it, just to give a demonstration of how powerful and expressive the STL is. There's a vector and unordered map here. Byte and file system path are upcoming features. I think they're both C++11 features, but some of them are still in the experimental subdirectory. But you can look at this and you can very quickly get an idea of what the writer is trying to do here. It's very expressive. So a non-goal is to maintain zero cost abstractions. We don't want to make the user pay for things that they do not use. And that's something that the STL does a fairly good job at. Okay, so to begin introducing you to CNL components, this is the one that started things off, the fixed point. This class does one very simple job. It adds a decimal point to an integer. That's pretty much it. It's got rather more code than I've listed here, but the full interface makes it behave mostly like the integer with which it's specialized, which is int by default. In fact, if you leave the defaults, you get something that behaves as much like an int as I can manage. This may seem surprising. Surely it should be more like a float. It's got point in the name, which is true, but it also has fixed in the name, and it's not often mentioned, but all integers are fixed point numbers. They just happen to be fixed and especially inflexible about where that point is. Okay, so here's how you use a fixed point to define a number. I'm using the modern style with auto and uniform initialization. That's not mandatory, but I will provide an example later on of where auto does make a difference and is kind of valuable. Anyway, so here n is an int. Basically, but it's only worth 8 bits. It's less than normal. So the actual value stored is 64, and then it's divided by 256, and you get 0.25. When you multiply it by an integer, nothing special happens. The result is just 64 times 5, which is 320. And 320 over 5 is exactly 1.25. It's really just, it's kind of a semantic distinction. It's just doing regular integer arithmetic. It's a very thin wrapper. Just like std array, it's only adding one little thing to an existing language feature. And that's, I believe that's a good thing. But to explain why, you need to know what you're letting yourself in for. So I'll give you some examples of the behavior of this type. Starting with the good news, a thin wrapper tends to give you the least costly abstraction. In this case, fixed point gives you the same performance as int, which is very hard to beat. Because we're essentially performing signed integer arithmetic, an optimizing compiler reduces this function down to something very simple. I mean, this is a canonical example of when it's a good idea to use a signed int. And the fact that there's floating point types involved doesn't matter. You always know with a signed int, if you add to it, you get a bigger number. Okay, and there's the assembler from Compiler Explorer. Okay, this so you can't see the. Fortunately, you can't see the source code here. Let me just drag that over. Which way is it? I don't know why this started happening. Okay, so here we see this is the same function written twice using the CNL library, and then just hand rolling the same thing with language level features. And the I version, function I, that's kind of what anybody doing fixed point arithmetic without the help of a library, they kind of have to write code like this all the time. It's a pretty simple example, but the aim is at all times to not incur any extra cost by using this library. It's just saving on a bit of mental arithmetic that's easy sometimes to get wrong. All right. I've got to find my cursor. Okay. Oh. Okay, so some not so good news now. Int is a sharp tool, and it's easy to cut yourself if you're careless with it. And a good example is if you actually do go off the end of the range that int provides. There's also, it's just as dangerous to do that using fixed point, because fixed point is not here to try and fix everything that's wrong with int. It's just here to scale ints by powers of 2. I'd like to share at this point one of my favorite C++11 features, which has a bearing here, and that's static assert. And anybody who's not using static assert yet, I highly recommend it. I use it a lot. You can, if you grep for static assert in the CNL library, I think there's now over 1,000 uses of it. And it's a great way to test your code. You can use it to test any constant expression, and it means you don't have to download a test framework or run a target with and use an assert macro. You just if your code compiles, your code is passing your tests. The first expression here compiles because the expression is true. The second one fails because the expression is false. But the third one fails because the expression is not a constant expression. Expressions with undefined behavior in them cannot be constant expressions. CNL uses const expr throughout, so most of it can be tested using static assert. And here, when I pass the form of these two fixed point expressions to static assert, it falls into the third category. It doesn't compile. It doesn't even come up with a true or false result. It just doesn't compile because it's not a constant expression. All right. Okay. Another example. So this is one that John Kalb gave last year in a lightning talk, which is that's pretty bad. 1 is not less than -1, but due to a quirk in the way that int is designed, if you're comparing, firstly, you can't compare two things that are different types. You cannot perform operations on them. They become implicitly converted before the operation is applied, so that they're both the same type. And so here you've got to choose between signed and unsigned, and there's no perfect solution here because they're two ranges that overlap. So for whatever reason, the default was chosen to convert the signed to unsigned. And when you convert from signed to unsigned, your negative numbers suddenly become typically very large numbers. And yeah, suddenly -1 is now not -1, and it's now way, way greater than 1. And that's with fixed point. That's not anything to do with fixed point really, other than it's fixed point of unsigned and fixed point of signed. It's an issue with integers that you just need to know about when you're dealing with integers. Okay. Right. So here, let's see. The answer is when you instantiate fixed point using built-in integers, these behaviors become they come along for the ride, as I said. I'll show you more of that later. But right now, I should mention there's a C++17 feature in here. Most of the stuff up until now was C++11, and in fact, the compiler explorer example from earlier, I actually managed to get as far down as GCC 4.8, but that compiler barely supports, well, it doesn't even fully support C++11. But here you'll notice, let's see, here is a fixed point declaration with fixed point types here, where I'm not using angle brackets to say what the fixed point instantiation is. This code here is identical to the above comparison. You notice I've added a u there, 1u. So the first of those two fixed point types, it's deduced as being fixed point of unsigned integer, and the second one is deduced as being fixed point of signed integer. Doesn't solve the problem with comparison, but it's one way in which CNL code can be more terse. Anyway, so that's the bad. So now ugly. This is going to be a foray into division. And I'm going to ease you in gently with some multiplication. So what do you get when you multiply fixed point values? Well, remember, this is just integer arithmetic under the hood. When you multiply numbers, you add exponents. So when we get a result with an exponent of, so we get a result of with an exponent of -8 plus -8 here, which is -16. Okay, so I'm going to use, I'm using static assert here to test that the result type is what I expect it to be. Another great example of static assert. I don't just use it to test that values are correct in, for instance, arithmetic operations that I perform. I also test that the types of those values is the same as well, and that's what isSameV is doing there. That's one of the type traits components that let you test types. So why not just convert back down to -8? I mean, the result of typically, and I'm going to perform some multiplication. I've got to store it somewhere. Very often, I'm going to put it back in n or something with the same type of n. So why not just -8? Well, that's extra work, extra runtime work. And it's also a way that you could lose precision. You're going to lose 8 fractional digits. What if your two inputs have different exponents? Which one do you pick? It's arbitrary. There's no right answer. These are some of the tougher issues I've had to wrestle with when designing the operators for fixed point. the bottom line is I'm trying to do as little runtime work as possible. And, oh, okay, so again, the compiler explorer hasn't quite come out the way I hoped. I may just leave it, actually. Yeah. And I'll tell you what I was looking at. Oops, hold on. Okay. Oh, it's here. Great. Okay. So, yeah, this is the same function again. So these are very toy examples. But here we're taking a floating point value. We're converting it to a fixed point type with 8 fractional digits. And then we're squaring the result, converting it back to float and returning it. Admittedly, in isolation, a fairly pointless thing to do. But this is a good way to actually produce some assembler. And you'll see that so the old way involves scaling by hand, doing some conversions back and forth. But also notice once you've squared n, the exponent, like I said, has doubled. And so you have to remember that while you converted from float, scaling down by 8 bits, you have to scale up again by 16 bits. And this is the kind of gotcha that hopefully something like fixed point can help avoid. In small sections of code like this, the CNL starts to look a little more readable and takes a little more cognitive load off the programmer. As the examples build up, it starts to get more and more advantageous. And you'll see, I think this is an example where the code is, yeah, it's identical. Okay. All right, more ugly. Okay. All right, so here we have division. Division, where multiplication adds exponents together, division subtracts them. So the exponent of the left-hand side operand minus the exponent of the right-hand side operand is what you get in the quotient, in the result here. So what we end up here is no fractional digits. So everything to the right of the decimal point in this result is 0, and that means we get 0 altogether because we're dividing our denominator is larger than our numerator, and that's like true of all. If you think about it, 50% of all integer divisions that you could do give you a result of 0, which is fine if you're kind of dealing in sort of whole numbers, remainders, that kind of thing. It's not really what you expect if you are using a type which you were hoping could replace floating point in some of your code. Here, yes, here I've to make up for this, I've added a divide function, and it does kind of what you would expect it to do. Excuse me, I just gotta close this and clone it again. Oops, wrong one. Okay. Okay, now I can see what I'm doing. All right. All right. So fixed points are just scaled integers. It doesn't magically make integer division work well for them. So yeah, this helper function lets you multiply like with multiply, you're getting double the number of digits when you perform a divide. We'll go deeper into the problems related to this. So say you get like a multiplication here, one integer digit, one fractional digit, and you multiply them by another number with one integer digit, another fractional digit. You get two of each now. Your result is twice as wide, and this is just as true for decimal as it is for integer. When you divide two numbers, it's similar but more messy. Firstly, it's easy to get something that's completely unexpressible with digital notation altogether. We could do with a fractional type at this point, and if anybody would like to write a fractional type, that would be great. If nobody volunteers, I would probably end up writing it myself at some point. And this is something that people have talked about adding to the standard also, and that would be great. So here's kind of some notation showing you roughly what happens with division. You see, you get the integer digits of your numerator added to the fractional digits of your added to the. Oh, sorry, this is multiply. You get the integer digits of your left hand and right hand side are added together, and the fractional digits of your left and right hand side are added together also. But with division, sorry, that should be a divide symbol there, not a multiply. You get kind of a switcheroo. So the integer digits of your quotient are the integer digits of the left hand side plus the fractional digits of the right hand side, the denominator, and vice versa. So things are roughly, you can expect your results to be roughly the same width, but the floating point might not be where you would expect it to be. And so that's what divide is doing here. That kind of explains why if you put in two 32-bit numbers, each with 8 fractional digits, you end up with a 62-bit number with 31 fractional digits. And that's because n has 23 integer digits, 8 fractional digits. So the denominator also has this many, and when you add them back together, this is the result that is probably the one that people are going to want. And it is a pity that this can't be the default division operator, but I've tried making that work, and there's just too many problems with it. In particular, if int if int is a different width on a different architecture, you're going to end up with very different results. And it'd be better if this is something that's portable. And so, in particular, say you're on a system where int is 64-bit, and that can happen. Also, there are systems where long is a different width. You're going to get more fractional digits in your result because the number of integer digits from the numerator affects how many fractional digits there are in the quotient, which will mean that you get genuinely different results. So you have to be aware of this when you use this function. This isn't a problem that affects the division operator. And I haven't used the C studint types very much, but if you're familiar with int32_t, uint 8_t, those can be very helpful for being certain about the widths of the integers that you're using. All right. So, elasticity. This is another feature of CNL. We have there's a fixed point type that cannot represent 1, and its range is 0. 0 to 1 exclusive, and its resolution goes down to 256. N is the maximum positive value of this type. And under the hood, N is most likely an unsigned char with a value of 255. I'm taking unsigned char 255 and I'm multiplying it by unsigned char 255. So what happens at runtime and compile time to NN, and does it overflow? What do you think? Actually, it's an int. You might expect that NN was going to be uint 8 because both of the inputs to that multiplication were uint 8. And this is not the case because of promotion, which is one of those strange behaviors of int that I would like to cover. Because you would, if you just had two raw uint 8s and you squared them together, you would get an int. And so, again, fixed point isn't trying to fix anything that is perceived to be wrong with the way that integers work. And this isn't necessarily even though it's a surprising thing about integers, it's not necessarily a bad thing. And in this case, it's good because we've avoided getting completely the wrong value here. Now, if we're dealing with larger numbers, then it's a disaster. We lose the top half of the number. This is signed overflow. This undefined behavior, you cannot put this in a static assert. If int was unsigned instead, it would be defined behavior, but the result would be totally wrong. It seems that what we want is an integer with consistent rules about how and when it promotes to a wider type. Hence, elastic integer. Is an elastic integer, it's probably going to resolve down to int with maximum value, but that, like I said, that varies depending on how wide an int is. Your architecture may vary, but here we know explicitly we've got 31 bits of integer here. So when I multiply this, I get something necessarily wider. It required 62 bits in order to be sure to store any possible multiply operation that could be applied to it, and that's exactly what happens. Oops. Note that when you add these two add elastic integer numbers together, instead of 62 there, we have 63, because when you add two numbers together, you need one extra bit to make sure that you don't overflow. It'd be a good time to point out that the CNL is just a bunch of other people's ideas pasted to look like a coherent library. The foundation of all of those fixed point operations was already figured out when I found it in Mateus Izvikov's FP library, and the credit for the idea of a type which automatically widens like this one, that goes back at least as far as Lawrence Krall's work in standardizing fixed point. He's been working on trying to do that for years, and he's also proposed combining these two particular features into one supernumeric type, and that's kind of the alternative approach that has been proposed for standardization. But I'm not done stealing other people's ideas. My main inspiration is the STL, and so, if these were STL types, what would they look like? What would this super type be like? I think it would be a composition of elastic and fixed point. Now, up until now, I've been composing types just using fundamental integers, so fixed point of int or elastic integer under the hood by default does also use fundamental integers. But in CNL, composition means a whole lot more than that. Here we've made a composite type which addresses two concerns in unison. The concern of tracking exponent is addressed by fixed point. The concern of ensuring results are wide enough is addressed by elastic integer. And when you perform multiplication with the combination of them, It just mostly works, which is really nice. You get something where the fixed point is taking care of the where the exponent should be, and the result is wide enough. And there is, apart from that, this is literally just two 32-bit integers being multiplied, being widened to 64-bit integers multiplied together. It's difficult to imagine how you could do that with fewer instructions in less steps, with less computation or less energy. Unfortunately, division isn't quite the same story for reasons we've already gone into. So you'll notice there I've got I'm pulling in a header here. It has an overload to the fixed point operator divide, which is specialized for fixed point of elastic integer, and it gets you back the result you'd expect from that CNL divide function that you saw earlier. So the idea is that for fixed point is very low level. It does one thing well, and it does have a few situations where, because float and integer division just are not the same thing, they just do different stuff. They go about things a different way, and there's no way to get around that. And integer division is not very good for situations with real numbers. However, elastic integer, it's kind of a bit more hand-holdy. It's the sort of type you want to use if you want to try and not worry so much about overflow, but in a way that generally is quite fast. Sometimes you'll find that you didn't really need to widen the type because the numbers you were dealing with were smaller than the full range, but elastic integer will give you a wider type anyway because it's being kind of thorough. And so here we have this compromise where fixed point elastic division is slower. There's a bunch of there's a shift that is required. Firstly, the numerator is widened, then it's shifted a whole bunch to the left. Then regular integer division is applied to the numerator. It's divided by the denominator, such that the result that you get back fits this type. And so it's complicated. It's a little slower than just integer division alone because there's a shift involved. But really, you should try and just generally avoid division if you can. Division is slow, rather like a square root is a lot slower than squaring a number. So division is a lot slower than multiplication, and that's somewhat inevitable. So given that, the fact that there's some extra shifting going on, it's probably not hurting anybody too much. And so I'm not completely certain about this design choice, but that's the direction I'm going in at the moment. If you want a relatively user-friendly but still really quite fast fixed point type, you should combine it with elastic integer to get all these benefits. Okay, so not everything, not all overflow and out of range errors can be solved at compile time. So we need some runtime safety. So what happens, for instance, when you mutate an existing value, you cannot suddenly change the type so that it's wide enough to fit the value. So here's a third type. It's called safe integer. Its job is to catch and handle runtime overflow conditions. It assumes you're using your integers to express quantities and that you don't want to exceed the range of those integers. In other words, even though exceeding the range of an unsigned integer is not undefined behavior, we're going to assume it's not what you intended to do if you use safe integer with an unsigned integer. So, okay, another pop quiz. What do you think happens when I add 1 to a maxed out 8-bit integer? it does seem like a trick question, but it shouldn't be. Once you understand the peculiarities of C++ integers, and once you understand what is required to write generic numeric types in C++, it should be second nature to expect the result of arithmetic operations to be int width. So in other words, there was no overflow here. If you thought this was just a newfangled modern equivalent to this, well, yeah, the auto here does make a difference. So if you look at K, we're actually imposing a second conversion that you may not often realize you're performing. So with J, I is being added. I is an 8-bit number, and it's being added to 1, which is a 32-bit number typically. So we need to promote I to a 32-bit number first before we perform the addition. So what we get is two integers added together, and just the result is directly assigned to J. And so I would say that's it means people are kind of surprised that J is int when maybe they assumed it might have been unsigned int. I mean, even if you added two unsigned int numbers together, you'd still get int. However, with K, it's doing the same thing. It's converting up to int, performing the addition, but before it assigns to K, obviously it needs to cast back down to uint8. And in some situations, that could incur a cost. And certainly, it's something where it's not. Is it necessarily helping you that you know what the types are, because it's not like you can read that and it's intuitive that there's an implicit cast going on, a conversion back down to 8-bit. I don't know. Anyway, there are situations where this can really kind of cause extra runtime processing to happen. Anyway, so with J, there was no overflow. There was no possibility of an overflow happening. With K, now this is where the overflow does occur, because we're casting back down. It's the fact that conversions happened here or there, or whether we used auto, is orthogonal to the fact that once we try and store the value 256 in 8 digits, doesn't fit, and we throw here. That's just the default behavior of safe integer. You can get it to do other things. You can say, I just want this to wrap around, or just do whatever's fastest, or terminate. Okay. Anyway, so when we try and, as I mentioned, you cannot have undefined behavior in a static assert. So here, where we try and do the casting back down to a smaller number, you'll get. Well, here we're trying to do a comparison between an 8-bit number and a 32-bit number, and I need to work on some of these errors a bit. But it's a situation where you can catch an error before your code is even compiled by passing it through static assert and seeing if there's any undefined behavior there. It's kind of a good way to test the thoroughness of your of the expressions that you're writing. All right. So one of the big C++ 17 wins for CNL is class template deduction. So I showed previously the class template deduction, where you have to explicitly say that this literal is unsigned. Here I'm saying it's unsigned long, and so the deduction guide can figure out that, well, that means we want fixed point of unsigned long, just to make sure that no matter what value is going in here, it's going to fit. But that's wasteful. Here we're passing in 128, and it's deducing that, well, 128 is an integer, so we're going to get a 32-bit fixed point value. So I've I've added user-defined literals to CNL. Excuse me. Rather like the literals in the standard library, you pull them in using a using directive like that. Actually, another error that should be using namespace CNL literals. By the way, please feel free to point out any other errors you spot. So the underscore C here, 128 underscore C. This is I've overloaded operator quote quote, which allows you to create new literals like this. This 128 underscore C here is going to produce an integral constant. There's various libraries that perform this type of trick. I don't know if you're familiar with stood integral constant, but if you are, it's a class template where one of the parameters is a non-type template parameter. In this case, the value of that non-type template parameter is going to be 128, which means the value is part of the type, which is pretty crucial here because with deduction guides, I can decide exactly what instantiation of fixed point Z is going to be, but I need to get that information from types. I can't just pass the value 128 into this constructor and get back, and from that figure out what the best type is. So in this situation, so 128, that's just one bit with a bunch of zeros after it, and so you can express 128 with a single bit. Z's got a value of 1 under the hood, but we have a positive exponent here. Notice it's positive 7. That means we have negative 7 fractional digits. If you can wrap your head around that, there's with fixed point. There's no reason to have only a positive number of fractional digits, or indeed integer digits. We'll maybe see that a little more as we go along. Okay, another example here. This is there's 40 zeros in front of this this value. In other words, there's no way that it can fit into a 32-bit number. But because we're using the user-defined literal, we can figure out here, well, this just needs 1 bit, and fixed point deduction guides by default go to int or larger, and so we just store this in an int with 1 bit that just happens to be shifted statically by 40 places there. And you can take this to ridiculous extremes. You can have numbers where you have 1 million zeros after the end of them. Obviously, you can't type in the literal that initializes them, but you can express them and work with them. So here, you can't do the same trick. We're using all the bits here. We're using 41 bits. And so the same deduction guide looks at this and says, well, I can't squeeze this into a 32-bit integer. So instead, it's a long value. It's a 64-bit fixed point value. And also, you need every last integer digit here. So the exponent's down to 0. But this is pretty powerful way to initialize numbers. This is just kind of the tip of the iceberg, what's possible in C++11 and beyond, and particularly the deduction guides where the angle bracket is replaced by a little bit of compile time work where it figures out what's the best type. It's pretty powerful stuff. There's a... this didn't come out quite right. But so here there's the elastic fixed point type, which I introduced earlier, is a little bit more difficult when you have composite types to initialize them from literals and to specify, well, I want this to be fixed point of elastic integer as opposed to fixed point of int or fixed point of safe int. So the way I've got around this here is by creating, well, we'll get to that in a sec. This is just elastic integer where there's a similar trick. It's taking the integral constant, figuring out that the value 2017 will fit in 11 bits. So that's the number of bits 11 figured out just from the value. And yes, now here we combine those two abilities. On the one hand, we're not wasting bits on the right-hand side of all the interesting digits, and on the other hand, we're also not using too wide a type. And so, but unfortunately, I've had to add a new user-defined literal. In this case, I've called it underscore elastic. And anytime you create a number with underscore elastic, it does both jobs. It creates a fixed point elastic type with all the right characteristics. So here, this is 7F000 is a value with 7 bits set to 1, and then just a bunch of 0 in both directions. There's 12 trailing zeros there. And so we're just storing this as value 127, where it's implicitly shifted by 4096. And again, this not such an exciting example, because you can fit this into an int on a good day with language level primitives. But again, you can take this to extremes. You can have numbers with arbitrary trailing zeros and store them in like really small spaces. You know, you can store values in the gazillions in a byte in certain circumstances this way. All right, so there's maybe a little. Yeah, there's. By the way, I frequently show examples of this stuff. You may have seen some of this on Compiler Explorer earlier, and I tweet some of the more crazy stuff I can do with these values. So I'd like to talk quickly about interoperability. A couple of libraries in particular that I've been playing with, making things interoperable with, because it's all about composability. I really want everything to not just fundamental integer types and the types from CNL, but other types from other libraries. I would really like to see them all work together, and often that's pretty easy to do. I've got some luck with Boost Multi-Precision. If you go to the documentation for my fixed point library and CNL, as soon as I write it, you see like a working example of where I've actually used multi-precision, fixed point of multi-precision to express a Google. So I take 10 and I take 1 and I multiply it by 10 100 times in a for loop, and I get Google out, which is not that big a deal because you can store Google in Boost Multi-Precision already. But then I can get the inverse of it to get a Google pretty easy. It's just like in one operation, and it's faster than it's slower than doing 32-bit division, but it works. Unfortunately, you cannot do a Google plex with Boost Multi-Precision or fixed point of Boost Multi-Precision, because the range 10 to the Google, that's beyond the range of int, and we need non-type template parameters here. But it's not bad. I mean, one with 100 zeros and it's nowhere near the kind of the limits of what can be expressed. Another library that I've had some success with is Boost SIMD. All I had to do was make one simple pull request to the Boost SIMD project, and I was able to write a Mandelbrot generator with the combination of these two types. It works pretty well. There's some sample code. I need to do some work with Joel Falcu, one of the authors of Boost SIMD, to get the performance characteristics out that I'm expecting. But SIMD integer arithmetic, there's situations where this could give you like very, very good performance and relatively readable code. So a few things that are on the roadmap. So by the way, here's the address of the library. If you're interested, I would greatly appreciate any feedback you have to give. There's a lot kind of missing still. Arbitrary width, I mentioned, you can get a 128-bit integers in Clang and GCC. You cannot in the Microsoft compiler. Incidentally, the AppCell library that was announced earlier fills in the missing 128-bit integer support. I haven't had a chance to test it yet, but that type also should work with CNL. But going to arbitrary width would be really great. Boost multi-precision does a pretty good job of that, but something simpler and more bare metal would be good, and there are efforts to standardize that ongoing. Full support for rounding and overflow. Please just ignore the comments there. But precision, sort of rounding and rounding and precision. I have barely got onto those, but we want to see free functions. So we have a safe integer and precise integer there. You don't always want to use a type. Sometimes you want to pass raw integers into a function to get the rounding and precision that you're after. We're going a little off the track here, I'm afraid. But there's a whole bunch of other things that need to get done. In particular, there's a lot of arithmetic operators that need to be written to support just a single type, like safe integer or precise integer. And then sometimes in combining these different types together, this unearths some things that need to get fixed in order to make the interoperability as seamless as possible. But I have managed to combine all of these types together to get a sort of like a super type that is approximates real numbers with any rounding mode you like, and it does whatever you want it to do when overflow occurs. And so if anybody's interested in trying this out or contributing or has any requests, I basically would like to develop stuff in the order that it's most useful. And so whenever pull requests or issues come in, I do try and address them whenever I can. Sorry I haven't left much time, but it's there.
One or two questions.
We've got time for a few questions. Yes, hi.
For the class fraction that you got somewhere in the middle of the presentation, have you tried using the rational integer library from the CNL library?
Yes, the question is, have I tried using stud rational? Yes, the problem with stud rational is that it's rather like integral constant. It is values actually in the types. So what is needed is something like rational, but which has variables in it that actually store these numbers. I don't think stud rational actually has variables associated with it. But yes, something a lot like rational. A lot of the stuff from the time library generally is a good example of how to do good numeric types. Yes, you had a question?
Yeah, so anything along the lines of a square root operation on these numbers or sine?
Right, okay, the question is, have I thought about writing a square root function or anything like that? I did write a square root function. There's one in there, CNL squared. And also I put placeholder, some trig, sin, cos, tan, that kind of thing. But it's, so firstly, this is one place where floating point really does shine. A lot of effort's gone into making fast math available on floating point units. Then when you try and write general purpose fixed point equivalents, you often find yourself choosing between different algorithms. Some are more precise, some are slower. So I've kind of, I've not made that a priority currently. Also, there's some interesting questions like, is radians for angles, is that the best scale for for fixed point types. It might be that we want a scale from 0 to 1 exclusive, and then we could use unsigned integers, and then we get the angle overflow for free. So you add two angles and they exceed 360 degrees. Well, you get a sensible result back out. So there are some open design questions there, and there's a lot of work involved. A lot of work has gone into a Boost fixed point library in that respect. But yeah, it's something. It's a big area that I do intend to get onto at some point. Yeah. Okay. Thank you very much. Thanks.